Hooke's law. So we can build up Hooke's law for orthotropic. And again, we apply superposition principle. So let us pick up that generic model. So here is the model, and I draw that one very schematically. Okay. So using the same coordinate system x, y, z. So here is substitute sigma x. So sigma x is obtained by dividing the loading by the area, and then we have the second loading conditions. So we have the sigma y, and then we have sigma z. So any generic loading conditions can be decomposed into the three subsystems. So we only concern about the subsystems here. And now for each case, we are going to calculate the strain in x, y, z directions. Now for the first case, here we can follow up this condition here. The strain, basically this is the strain in x direction. Okay, so that will be the stress divided by Ex. Okay. And this one, what is this? So this one we can utilize that equation here. That basically is basically here we can say this one epsilon y equal to minus mu xy times epsilon x. Okay, let me rearrange in this way. Okay, so we're picking up that one. So basically this one is equal to the strain in x direction times xy. So basically this is the axial strain, and axial strain and multiply with Poisson ratio, axial strain together with the axial direction in the y component. The reading is like this. Okay, so don't be confused by the symbols. Let me say this again. This is the axial strain, x direction. Axial strain in the x direction induce the y component. Okay? Okay. And now the same thing, the axial strain induced and z component. But okay, like this one. And now for the second one, yes, for the second one we like to fix the axial strain. The axial strain right now for the second case is in the y direction. So in the y direction, this should be written by sigma y divided by Young's modulus, what Ey. In general, that shouldn't be equal to Ex. Good. Now again, we follow on that our notations minus the sigma y, the axial strain, times the axial direction y, and in the component x. Okay, and the same thing for here, the axial strain, and times mu, the y axial directions in the z component, mu z. Okay, and now for the third one. We start with the axial strain. And then here the minus the axial strain z divided by Ez. And again, the z is in the axial direction. We're looking into x direction, zx. And here is minus z, zy. Okay? So now we have those things, then we simply take the summation. So take summations is for each one. So now for epsilon x is under superposition principles, we simply sum up the whole list. So that will be here kind of a little bit too writing, so let me do this carefully. Sigma x dx minus sigma y ey mu yx minus sigma z ez mu zx. Okay, and epsilon y will be equal to sigma. I'd like to take the leading term as a positive, so as an axial term. So here is ey, okay, minus x dx mu xy. So this is the first portion of Hooke's law. And then for shearing rigidity, that is very straightforward. And we simply is this tau xy divided by corresponding and tau xz gamma, tau xz divided by gxz, and gamma yz equal to yz divided by gyz. That's it. So under these situations, we in total
And that's shearing stress?
these are shearing stress and shearing strain. These are shearing stress. Top. Okay. So in total, we have 6 equations. So basically, if you like to write it up, let me try to write it up. So Hooke's law will be given by this. You don't have to write this one. I just want to show you the content, but the what is here. Okay, so epsilon at epsilon y, z, gamma x y, gamma x z, gamma y z. So everything, let me put it down here. So that would be ex minus mu yx, ey minus mu bx ez 0, 0, 0. And here is tau sigma x, sigma y, sigma z. These are matrix multiplications. Tau x y, tau x z, tau y z. And this one, you don't need to write, okay? So here it has 3 by 3, 6 by 6 matrix. And now again, I want to compute this portion is this. In total, we have 12 elastic parameters. And among the 12, the 3 are independent of the other 9. If we look at these matrix, we know that this matrix must be symmetric. and that is due to the properties of the anisotropic material. This matrix must be symmetric.